Alright, welcome back everybody. Glad to see you again. This is note video number 11. Alright, this is the second note video that is happening in Physics 3. And in this one, we are going to be talking about how machines work. So a couple of quick reminders. Machines work, or machines themselves, make working easier. Well, if they make working easier, what is work? Well, work is part of this equation that we've learned. Work is force times distance. If you remember, we measure work in joules. It's force times distance, newtons times meters. Well, how is it that machines can make work easier? Well, machines must have something, they must impact in some way one or both of these two factors that derive work. So let's take a look. If the amount of work here, if this value stays the same, but to make the job easier, the machine reduces force, what has to happen to this value? So if this is the same, this is smaller, distance then has to get larger. And that's, in a nutshell, how machines work. We could just end the note video right now. Machines work by either increasing the distance to decrease the force, or increase the force to decrease the distance. There's really no other way to go about it. One of those goes up, the other one goes down. The way to go about doing that, though, is numerous. So we're going to take a look eventually at lots of different machines and how they play with this value of distance and force to make work easier. So if the force goes down, that must mean the distance must go up. A good example of that is a wheelbarrow. Think about what we use a wheelbarrow for. We use a wheelbarrow to move heavy objects around like a yard or a construction site, or to move heavy objects from one place to another. These are objects that typically are either difficult to carry, like a whole bunch of gravel, for example, or something that's really heavy, like a bunch of cinder blocks that you can't pick up and carry across your yard. Well, how is it that a wheelbarrow works? Well, let's say we put a really large, let's say we put a really large rock in here. And I want to lift it up in order to move it. Well, when I lift this handle, the handle might lift this far, but the rock is only going to then go up that far. Notice I am moving the handle significantly further than the rock is going. So the machine works by increasing distance to reduce the amount of force that it takes to lift the rock. So if this rock was so big that I couldn't lift it normally, if it's already in a wheelbarrow, I can lift it pretty easily. It actually is an example of a lever that we will talk about in the next note video. Or in a couple note videos, I should say. Well, what if the amount of work stays constant again, but now over a shorter distance? What if I am not moving as far as I normally would? Well, if that was the case, if distance goes down, that means force must go up. And that's how a sprocket on a bicycle works. So if you have a bike where you can change gears, if you notice in the back part of the sprocket here, you have a big set of gears, a big set of tooths, and then inside you have a little set. Well, when you go from the big set to the little set, when you change gears to the smaller sprocket, you have to pedal with more force because there is less distance here. You are applying that force over a smaller circumference, so you have to pedal harder to get the big wheel to go around. So you can, in the end, end up getting more speed that way, but it's not the way I'd like to climb a hill. Well, what if the amount of work stays constant and the distance stays constant? How would this be a machine? Because if the distance stays constant, that means the force stays constant, that means the work stays constant. So how is it that machines could be making something easier if we're not changing either the force or the distance? Well, it's a little bit like how we talked about velocity and acceleration. There's another component. It's kind of a hidden component here, and that is direction. Sometimes you make a job easier by changing the direction that you're applying the force. And that's what a pulley does. Pulleys work by, because sometimes maybe it's easier to pull down than it is to lift up. So we can throw a rope through a pulley and attach it to the object, and then we can pull down on the rope to make the object go up in the air. It would take the same amount of force to pulling down as it would lifting up, in this case with a single pulley, but we're just changing the direction of it. This is the big key part of understanding machines. It's mechanical advantage. Big, huge star here for the mechanical advantage vocab term. You definitely need to know mechanical advantage. We are going to be calculating mechanical advantage and then using that calculation in lots and lots of problems moving forward. Mechanical advantage, simply put, is what a machine does to turn you into a superpower. You become superhuman, you're a superhero every time you use a machine because you're able to do things that a normal, mortal human being cannot pull off. Because machines multiply your force. Mechanical advantage is the number of times, the number of multiples that the machine increases whatever force that you put on it. So imagine if you could exert 100 newtons of force. All right, or like 400 pounds of force. Like you're a big guy. You can push like 400 pounds of force on something, or a big girl. And as a result, though, 1,200 newtons of force ends up getting applied to something. Wow. 400 pounds of force is a lot. 1,200 pounds of force is superhuman. Well, that's what machines do. Machines take what we can already do and magnify it. So here's the equation for calculating mechanical advantage. I'll often refer to mechanical advantage just as simply MA sometimes. If I want to know the MA of something, that means mechanical advantage. Well, to calculate the mechanical advantage, you take the output force, which is the amount of force that the machine is putting out, and you divide it by the input force, the amount of force that you're actually putting into the machine. So what would this look like in a math problem? Let's say you're using your can opener in your kitchen. You didn't think a can opener made you superhuman, did you? Well, you think you could, I don't know, tear the can open with your hands? Chew it open with your teeth? Something's got to be done to take open that metal container. Fun fact, cans were invented years before the can opener was invented. I find that to be very interesting. Apparently they didn't need to figure out how to open the can until they realized they couldn't get anything out of them. But anyway, your can opener takes 10 newtons of force to use. All right, so it only takes 10 newtons of force that you have to turn that little dial if it's a hand-operated one, or we can even pretend that it takes 10 newtons of force to push the little button on your electric can opener. But it ends up putting 30 newtons of force on the metal of the can. So, quick math, 30 newtons of force is the output, 10 newtons of force is the input, 30 divided by 10 gives you a mechanical advantage of 3. This is where you go, Mr. Reagle, you forgot your units. You've always said you always have to have units on a number, and a number without units is not a correct answer. Well, mechanical advantage is a little bit like slope in this way. Mechanical advantage doesn't have units. It's a multiplier. So notice Newton in the denominator, Newton in the numerator, Newton in the denominator, cancel each other out, so there are no units to put on there. So mechanical advantage does not have a unit. So let's meet the simple machines and call this video to close. What's this one? We have a long bar. We have this thing called a fulcrum that the bar pivots on. We have a load on one side, we apply force on the other. This, of course, is a seesaw, or I mean a teeter-totter, or I mean a lever. You guys have all played with these kinds of simple machines. Now, when we explore levers, though, we're going to talk about different kinds of levers, because these three components are a part of every lever, but we can move them around and rearrange them. Sometimes we have the fulcrum out here and the force in the middle. Sometimes we have the fulcrum over here and the load in the middle. They're all different kinds of levers, and we'll explore all of those later, but all of them are levers. The second kind of simple machine is called, you know this one? We have a big disc that turns, and when the big disc turns, the long rod also turns. This is called a wheel and axle. Now sometimes the input is on the wheel, like in a car you would turn the steering wheel and that would cause the axle to then turn, which would then cause the tires to turn. Sometimes though, you turn the axle to make the wheel turn. Sometimes you see things like that on clocks, for example, how the hands of the clocks go around because the axle on the inside is being turned. This one, we talked about it already, is a pulley. So pulleys, you pull down on one side, it lifts the load up on the other. This is a simple single pulley, but pulley systems get a lot more complicated. And we're going to talk about how to solve more complicated pulley systems. Things like ships and other kind of like places where you have to lift and haul heavy items or move things around. Theater crews often have very complicated pulley systems to raise and lower the different things that go on stage. You might call this a ramp, but science, we call them inclined planes. An incline means something is tilted, and a plane in math is a flat surface. So this is a tilted flat surface. And it's the first of the simple machines that we are really going to take a look at when we start looking at those note videos. Here we have an everyday object that I hope all of you could recognize. This is a screw. So a screw is a cylinder that has, if you read the definition in your book, the book says a screw is an inclined plane wrapped around a cylinder. We have a couple of activities that we're going to do in class though, and we're going to explore what a screw really is and how it works. This one is a wedge. So you can think of a wedge as like a knife, like if this was a piece of steak and we were cutting through it with the knife, we're using it as a wedge. Wedges are my preferred way to split wood, well, unless I had a log splitter, but instead of using an axe, I use a sledge and a wedge. So you take a wedge and you start to pound it down into the log, and then you use the sledgehammer to beat down on the wedge, and that splits the wood. I find it much more useful than an axe. And those are the simple machines. That's the end of the note video. We have 16 questions. Most of these are going to be identifying simple machine, but I might also give you questions where you have to figure out the mechanical advantage based on the input and output. Or if I give you a scenario and I say things like, if the work is the same and the distance went up, what happened to the amount of force? Have a good day.